Hello, everyone. My name is Hans Mertens. I'm a PhD student at the Robotic Space Exploration Lab of the University of Hawaii at Manoa, and I'm presenting on a comparative analysis of uncertainty quantification models in active learning for efficient system identification of dynamical systems. Why do we want to do active learning for system identification? In our lab, we work in space exploration, and me and other members specifically work with rovers. And those rovers we want to deploy in unknown environments where we generally don't have a lot of training data. So what we're trying to do is to design algorithms that work well with limited data and with a minimum number of samples. And to this end, we have compared different uncertainty quantification models that we can use in our active learning algorithms to perform efficient system identification. How does active learning for system identification generally work? We have this iterative algorithm where we train either a Gaussian process or a Bayesian neural network model in each iteration. And what's nice about these models is that we can query the model and ask it, out of all the possible inputs I'm presenting you here, which one of these are you most uncertain about? And then we select these inputs because we expect the model to gain the most information from being trained on this input down the line. We then feed the input through our dynamical system and measure the system outputs. And using those input-output pairs, we can build data sets. Our inputs are our state variables, and if it's an actuated system, also our actuation at time t, and our outputs are our state variables at time t+1. And in doing so, we can train our model to predict how our dynamical systems forward propagate in time. And we keep retraining our models until we hit some stopping conditions where we believe that our models are sufficiently well trained to be used in the application that we care about. We have looked at 3 different kinds of uncertainty quantification models: Gaussian processes, which are kernel-based methods, where we've looked at RBF and Mertens kernels. And Gaussian processes are also generally the benchmark for models in this domain. Ensemble neural networks, we train multiple neural networks in parallel, and then we use the disagreement between the individual model's prediction as a measure of uncertainty. For Monte Carlo dropout neural networks, we only have one neural network where each neuron is associated with a certain dropout probability. And instead of feeding an input through our model only once, we do it thousands of times. And in every run, different neurons will be active and inactive, and we will generate different outputs. And in doing so, we can create a distribution over our outputs with a mean and variance. And this variance we can use as a measure of uncertainty. For dynamical systems, we've looked at the actuated pendulum, the damped pendulum, double pendulum, the Lorenzo tractor, and the two-tank system. So we have systems with different characteristics, with chaotic dynamics, non-chaotic dynamics. We have passive systems and actuated systems. We have systems with a smaller and larger input and output space dimensionality. We have systems with very simple dynamics like the damped pendulum, and also systems with complex dynamics like the double pendulum, which are generally quite difficult to learn for machine learning models. If we look at the most simple dynamical system that we have considered, which is the damped pendulum, we can represent the dynamics of this system with a phase portrait. And the phase portrait shows the evolution of trajectories in state space, which in this case is theta and omega. So the angle and the angular velocity of our pendulum. This is shown on the left side of this plot. In the back, we have the ground truth. The colorful arrows are the model's predictions, and the red crosses are the training data points. In this case, we're using a Gaussian process as our uncertainty quantification model. On the right side, we will see the test error and the variance of this Gaussian process. And when we are performing active learning, we want to see that our model can represent the face portrait as best as possible, and this will show us that it will have learned the dynamics of the system. And what we see is that it only takes our active learning algorithm about 12 iterations to converge to a test error of pretty much 0 and to represent this face portrait quite perfectly by strategically selecting informative inputs. We have evaluated our different models across 3 metrics, which are samples until convergence, runtime until convergence, and accuracy upon convergence across our different dynamical systems. And we have this large table in our paper where we show every experiment that we have averaged over 10 different trials. But for the sake of this presentation, I'm gonna jump to what works best instead of all the details. And what we've seen is that Gaussian process models work best across the board. So they are the most runtime efficient models for all systems. And for 4 of the 5 systems, they're also the most accurate and the most sample efficient. Only for the double pendulum, the ensemble neural network model was the better choice. And we see this here in this plot on the right side, where we have the test error plotted over the number of iterations of our active learning algorithm. And what we see is that the ensemble neural network model requires only about a third of the training data points that the Gaussian process models require, but still converges to a more accurate solution. On the left side, we see the same plot for the damp pendulum, and we see a similar phenomenon for all the simpler systems where the Gaussian process models work really well. They require a low amount of data and converge to very accurate solutions, and the neural network models are less suited for these kinds of simpler systems. The Monte Carlo dropout neural networks did not perform well for pretty much any application. They required a lot of training data and still performed worse and still converged to less accurate solutions than the other alternatives. A training mechanism we've investigated is what we call continuous training, where instead of initializing the model with random or default weights, we've used the learned parameters of the previous iteration. So for a Gaussian process, we would initialize the model with the length scale that was trained in the previous iteration. And for a neural network, it would be the weights and biases of our neural networks. And in doing so, we gained quite a big performance gain, especially for the ensemble neural networks, where we've seen 50% up to 100% improvement in sample efficiency, 100% meaning the model did not converge without this. And we definitely recommend using this technique for these kinds of models. For the RBF Gaussian process models, we also saw an increase in performance. For the matern kernel models, however, we saw a slight decrease. And for Monte Carlo dropout, we saw a huge decrease generally, but those models did not perform very well anyways. To conclude, no model works best across all metrics and for all systems for every application. So what we've seen is that Gaussian processes work really well for more simple systems with low dimensional inputs and output spaces, but for the more challenging tasks, continuously trained ensemble neural networks are a really good alternative. Monte Carlo dropout, we do not recommend using, and we did not see any kind of good application where we suggest those. For future work, we're looking also into experiment design currently, where instead of recommending an input to a dynamical system, we would recommend a initial condition or experiment parameters, which could either be in a simulated environment or a real experiment. And also we're looking into hyperparameter optimization for the ensemble neural networks, where we have a meta-learning outer loop that recommends hyperparameters and tries to minimize some cost function like samples until convergence or test error or something like that. So thank you very much. And also thank you to the NSF AI Institute in Dynamics for funding this work.